welcome back. We are going to push on in our preparation to understand this notion of relative frames and paravectors, and also the notion of Lorentz transformations, the Lorentz group. And we're at a very important juncture because we've gotten through many lectures about geometric algebra, but we have not discussed its most critical, its most often cited beauty, which is how it handles rotations. And specifically, how it handles orthogonal transformations of any kind, but also how that study of how it handles orthogonal transformations is easily generalized to how it studies how you handle Lorentz transformations. So now that we've taken a step into three-dimensional geometric algebra, I think we'll use that as our springboard to study this question of rotations, and then just try to move on with our paper. But this is definitely worth doing, and it's a bit technical, but it is fun because there is a bit of lights turning on. What we're probably not going to do is compare head-to-head how geometric algebra's rotations compare to rotating things using a formalism of quaternions or of matrices. That is an interesting issue because the theory is that this is so efficient that we should change all of our graphical computer programming code into geometric algebra to take advantage of how smoothly it handles the notion of orthogonal transformations. And but we're not going to investigate that, although it's really tempting. We're going to just focus on the physics if we can. Okay, so let's begin. So having never taught this before and having gone through a lot of different approaches, read a lot of papers and studied a lot of course materials about this from others who are much more knowledgeable about it, I've chosen the following path through this. First, we're going to study the normalization of a bivector. Then we are going to see how we can create a pseudoscalar for an arbitrary plane in any dimensional space, although we'll exemplify this in our standard three-dimensional space. So we're going to take our geometric algebra, which is three-dimensional, four-dimensional, 10-dimensional, and understand that we have arbitrary planes in there. And each plane can be given its own pseudoscalar, and that pseudoscalar will be very critical for us understanding how to rotate, to define rotations. Because rotations in geometric algebra are defined with a plane. We pick a plane of rotation. We don't pick an axis of rotation, and that's a critical point. The planes of rotation are sufficient to lock down what a rotation means. An axis is only sufficient to lock down what a rotation means in 3 dimensions. So we always talk about planes of rotation in geometric algebra. Then we will discuss the mathematics of bivector exponentiation. This shouldn't be too tough because we've actually explored this already. When we talked about the canonical form of a bivector in our previous work. However, we're going to focus on just how this applies to rotations, and then we'll start talking about general rotations. Now, what's not in this list is the notion of reflections. That is the idea that any rotation involving a particular plane can be understood as a collection of reflections. And that's actually a pretty useful way of doing it. However, I feel like it's not necessary given our level of understanding of how to handle geometric algebra now. We can go through the proofs without reflections. However, when we're done, we will reflect on what we've done. And if we feel like a little extra approaching the same topic from a different direction would help, we will do this reflection. There's no limit in how much time we can spend on this. This is a free-form set of lectures, so we can approach the same subject in multiple different ways. Okay, so let's begin with item number 1. Okay, so what I mean by normalization is actually, I suppose, more correctly said as orthogonalization. We could do that first, right? If I take the wedge product of two vectors, so v and u are now vectors, so I'm not going to throw down these little vector symbols here. Everything here that we're depicting is a vector, right? So v and u are vectors, and they're arbitrary vectors. So any two vectors can clearly be used to define a plane, right? We just create the vector v, see the vector u, there I am using the little arrows. See, I can't help myself sometimes. And this will definitely define this little plane that is between them. Now, especially if we wedge product them, then it's literally this plane element, according to how we view and understand our geometric algebra. So the question is, well, we already know that elements, plane elements, the shape is sort of irrelevant. What we're actually, this wedge product is really talking about this plane in a very abstract way. And it's not literally talking about this particular parallelogram. That is the way we can model it quickly in our head, so we can say, oh, the area of this parallelogram is the magnitude of this bivector. But it's really just the orientation, the plane orientation in space, and the area together define the bivector. So this is completely equivalent to any other bivector that has the exact same orientation and the same area. And so, of course, the idea is that I want to find a bivector where I have W and S, where W and S are actually orthogonal in this sense, right? That the contraction, the metric contraction between W and S is 0. That's what orthogonality means. And yet it defines precisely the same plane, which means that W and S, the area of W and S, is actually equal to the area of this parallelogram for U and V. And although I've drawn W and S little parallelogram smaller here, presumably I guess it would be a little bit bigger, but the important part is that W and S must lie in the same plane, right? So you need to think of, although my artwork here isn't particularly good, maybe I can improve it. Hold on. Something like this, right? U and V define a plane, W and S lie in the same plane, but they're orthogonal, which means this is 90 degrees, and of course U and V can have some arbitrary angular relationship. And the area is defined by the square produced by W and S and the parallelogram produced by U and V. These two areas have to be, the area of this object and the area of this object are the same. Okay? So that is, we can always do that, right? That the point is of this lesson is that this is a true statement straight up. The question is, can we calculate a W and S every single time? And the answer is pretty clearly yes, because this wedge product, when its contraction is 0, is simply the geometric product of W and S. So now all I have to do is choose S to be the inverse of W, V wedge U. And if I do that, what you'll see is the definition of the inverse of W is W over W squared, right? Because if I take the geometric product with that, I get W squared over W squared, and that's 1, right? If I take the geometric product of this W inverse with W, I should get 1. And you see that you would end up with literally W squared over W squared, which is two real numbers dividing each other into two of the same real number over itself, right? It's 1. And then you have this V wedge U, and we can now blow this up, right? And when we blow this up, remember, this is that case where it's the geometric product. This is a real number down here, so we really are worried about the geometric product of W with the bivector V wedge U. But we know something important. By definition, W lies in the plane of V and U. So W is in the plane of V and U. So W is linearly dependent on V and U. So we know right away that W wedge V wedge U equals 0, right? Because W is not dependent. W is dependent on both V and U. So because of that, the only part that survives is the contraction part, and we've memorized how to calculate the contraction part. So you just choose S to be this, and you've now met all the criteria. So whenever we see a bivector defining a plane, we can always automatically say, oh, well, I'm just going to move to two different bivectors, W and S, and I'm going to take those two bivectors and simply take their space-time product, and that will be the same bivector as V and U. We can always do that. So what I really want to always be able to do is say, you give me a bivector V wedge U, and I give you a geometric product W and S that is the same bivector. Now we can go one step further actually, because V wedge U has an area to it. So I could, in principle, go now, well, I'm going to normalize W and normalize S, right? So now that means W squared equals S hat squared, which equals 1, right? And then I'm just going to multiply by A, where A is the area of this parallelogram, right? Which is calculated through that determinant method that we used earlier. So this allows me to even go one step further, which is truly a normalized plane element, right? So W and S is now a normalized plane element, which brings us to our second topic. That is, we can create the pseudoscalar for an arbitrary plane, right? So the pseudoscalar for an arbitrary plane. So what do we mean by that? Well, let's take our unit vectors that we just created, omega hat, W hat, S hat. That's going to be our plane's pseudoscalar. It's a unit. So this is by construction, it's equal to omega hat wedge S hat, right? But because they're orthogonal, we can say that. But what is omega hat S hat multiplied by, I keep saying omega, but I mean W hat S hat, right? What does that equal? Well, that equals minus W hat S hat, S hat, W hat. Because of the orthogonality, right? Because W and S are orthogonal, we can now anti-commute them, right? That's a really important manipulative tool that everybody should be very comfortable with by now. But this is simply going to be minus omega W squared S hat squared, which in our Euclidean system, right? In our Euclidean system, the way we created W and S, right? The way we created W and S is such that they will be unit vectors, right? So this is going to be minus 1, right? Oops, minus 1. So if we redefine this as, let's say, little I, right, then we would have little I squared equals minus 1, right? And of course, this applies for the obvious planes in, say, three-dimensional geometric algebra, right? We have E12, E13, and E23. Each of those square to minus 1, right? Because E1, E2, E1, E2 is minus E1, E1, E2, E2, which is minus 1. And you can do this for all three of these, and you'll see that each of these square to minus 1. So we would say that E12 is the pseudoscalar of the 1-2 plane in three-dimensional space. E13 is the pseudoscalar for the 1-3 plane. But what's beautiful about this is I could take any plane in three-dimensional space and create a pseudoscalar for it. I just need two orthogonal unit vectors lying in that plane, and I've got a pseudoscalar for that plane. Okay, so that's done. All right, so now we will go down the road of bivector exponentiation. There's a few preliminaries. it's important to understand how vectors in the plane of a bivector uv and vectors perpendicular to a plane of bivectors u and v behave vis-a-vis the bivector. We have to get kind of comfortable with this because this is one of those facts we're going to use a lot. It's always very common to split a vector into the orthogonal and the parallel component. We've done this a few times in different parts of this material already. So let's consider just a vector A that lies in the plane defined by the bivector of u and v. And what we want to show is that if a vector is in that plane, then the geometric product of that vector with the bivector, that geometric product anti-commutes. And we want to show also that the geometric product of a vector that is orthogonal to the plane of this, that is orthogonal to the plane, that vector commutes. Now, in three-dimensional algebra, it's clear that B and any other vector that is orthogonal to the plane is going to be along B. But in higher dimensional algebras, B could be any vector that is orthogonal to the plane. There will be many different vectors. In 10-dimensional geometric algebra, we've already gone through this, right? The reason you can't have cross products in higher dimensional algebras beyond 3 is, with some technical exceptions perhaps, is the fact that you can't uniquely identify a single vector that is orthogonal to a given bivector. However, just because there are many different vectors that are in principle orthogonal to a given bivector doesn't mean that they are not orthogonal. They're all orthogonal. They're just not linearly dependent on each other. So these things are true in any dimension. We're just visualizing it in 3 dimensions because that's where we're sort of stuck. But let's prove these two things. I found it kind of fun to do the proof. There's an easy way and a hard way, and we're going to do it the hard way. And the reason we're going to do it the hard way is this is the kind of practice we need to sort of understand how to get comfortable with geometric algebra. Our goal is to get comfortable with this stuff. So, okay, so consider A, which is in the plane defined by the bivector u and v. This is tantamount to saying that A can be written as the metric contraction with u times the vector u and the metric contraction with v times the vector v, right? This is obviously the part of A that is parallel to u and the part of A that is parallel to v. These are just breaking A up into its components where we're using u and v as two components. So then I can write down what we're after. We're interested in this geometric product of A with the bivector u wedge v. So if I write this as A sub u and this as A sub v, just to simplify things, then we just simply make the substitution, and now we're going to start attacking this piece by piece. And using the linearity of the geometric product, I get A u geometric product. This is a real number, of course, so it's u geometric product of u wedge v, and another real number, v geometric product of u wedge v. Notice we haven't taken u and v and done any normalization. U and v do not have to be orthogonal to one another. They just have to be two vectors that define a plane. And by the way, the simple method does do that, does change u and v to some orthogonal vectors. But we're going to persist with this. So now we're going to use our famous expansion of this vector bivector product, and knowing that u is the inflation piece is going to be 0 because you have two u's here and two v's here. We're only going to have the contraction piece. So this is the contraction of this geometric product, the contraction part of the geometric product, and this is the contraction part of this geometric product. So that's all you need for this equality. But notice you could, for completeness' sake, and this was tricky for me to figure out, but you can include the inflation part, but you understand this term here is obviously 0, and this term here is obviously 0. So adding this in is basically just adding 0, right? So I'm just adding 0 there. But that will allow me to make it really clear that, this geometric product is this piece here plus all the way over here plus this piece here, right? And likewise, this geometric product is this piece here plus this last piece way out here, and these two, of course, are 0. Okay, so the next line, I tried to do the obvious thing, which is to, u dot u is 1 and v dot v is 1. And now I can combine these and get this. Turns out that was sort of a dead-end path, so let me erase that. I find these proofs using purely proper forms they're actually kind of pretty tricky because you've got to insert stuff and remove stuff. Like for example, I've inserted this because I eventually kind of figured out it was useful, but there were plenty of false starts, right? Anyway. But what I will reorganize is this structure right here. We're going to just sort of flip them around and change the sign and box it together. So I now have minus AU V dot U. So I commuted V and U because, this dot product commutes. And I left U dot U in there. And likewise over here, I have AV. I left the V dot V and I commuted the U and V together. Right? And then I think I also went as far as these sort of dud pieces, right? These dead pieces. I changed the sign and I made some commutations here. So instead of UUV, I have UVU, and instead of VUV, I have UVV. So I introduced some minus signs there. And then by doing that, first of all, now after that commutation and by pulling out that sign, this here is actually the contraction of the space-time product of u wedge v and u, right? That's the contraction part of that space-time product. And this is the contraction part of u wedge v with the space-time product of v. So this and this we're kind of doing the reverse. We usually are going from here to blowing it up and saying, okay, what's the vector? What is the contraction part of the bivector u and u wedge v with geometric product with u, and we derive this. But now we're actually going backwards. We're going backwards. And then we still have these two 0 terms, right? But understanding that these two 0 terms exist, I thought was important to help me understand, this and this, these are the opposite of the space-time product of the bivector uv with u times a factor au, and uv with v times a factor av. If you look at the form of these things, you can combine this with this and this with this to get this and this, which is cool. That's the idea. We're reconstructing a space-time product. Now, we kind of started that way, right? But we started with A on the left and UV on the right, and now we've got UV on the left, and we have a vector on the right. So we're headed kind of in the right direction. But what I'm going to do is I'm going to use the fact that AU and AV, they're real numbers. So I can pull out the bivector. I can pull that out front, and what's left behind is AUU AVV, which is the definition of A. And this minus sign is still floating out there. And ultimately, if you look at this, we ultimately have this minus bivector times A. So that's ultimately what we've shown, right? Is we've ultimately shown, if you go all the way back to the beginning, this guy, if you put it down here, equals A U wedge V, which is what we're trying to show. We're trying to show that the bivector u wedge v and a, remember A is in the plane, right? That was really critical. Where was that critical? It was critical when we made this substitution, by making the substitution for A in terms of its component forms of u and v. That allows us to go from this step to this step, to just the contraction, and noting that we can add this part in freely because it's 0, right? Without A being in the plane, that wouldn't have been possible. So we've shown that a vector in the plane defined by a bivector commutes, its geometric product anti-commutes. Now you could go through this entire exercise again with B, where B is not in the plane. B is its own vector. But we're going to use a different method, right? We're going to use a different method, right? Look how quick the proof is when you go to a normalized system, right? So I say the geometric product of A with a bivector, and remember A is coplanar with the bivector. Well, now I'm going to say, well, I'm going to rewrite this bivector, right? UV, I can always write U wedge V, it equals some other two vectors, remember W wedge S, right? Now, I can pick one of W and S freely, so I'm going to just pick W to be A, right? And I still know that I can find an S, right? I can find an S that is orthogonal to A, and these are the same, they represent the same bivector. I've shown you how to do that. We kind of did that here, right? Remember I did u dot v, just change W to A, and this is how you calculate the value of S, right? We've just done it. So with that in mind, I can write u dot v as A wedge S, right? And once I realize that A and S, hey, they're orthogonal, then this wedge product actually equals the geometric product. So I replace the wedge product, this wedge product, I just replace with this geometric product. But it's a geometric product of vectors that are orthogonal, so they anti-commute, right? So I just add this minus sign and I switch the two around, which is very nice. And A and S are, these two A and S's, that's still orthogonal, so I can replace them with their with its wedge product. But because of the construction of A and S, that's equivalent to U wedge V, right? So there, I've already just proven in 2 or 3 steps that a vector that's coplanar with a bivector, the geometric product of those two, anti-commutes. And you can do this very easily for the opposite circumstance, right? Where you're now dealing with B, which is not coplanar, right? B is orthogonal to U wedge V. So I do the same thing. I replace it with W wedge S. Now I don't have A, because B can't be part of this wedge product, right? Because B is orthogonal. So I just take any two orthogonal vectors, W and S, and I make the switch from U wedge V to W and S, which we've proven we can always do. And then once we've done that, we realize, W wedge S, that's simply the geometric product. But now B is orthogonal to W and S. So B anti-commutes with W, so I make the swap there and introduce the minus sign. And then B anti-commutes with S, so I lose the minus sign, and then I get WSB. So BWS equals WSB. And then you just undo it, right? WS becomes W wedge S, because W and S are orthogonal, so its contraction part is 0. And then you're left with, then you just replace W and S with the original parent vectors for the this bivector, and you get U wedge V, and you see B of a perpendicular, or a vector orthogonal to the bivector U wedge V is commutes with the bivector. So now we can understand this, and the reason this is so important is because what we're going to end up doing is we're going to be picking, some, ultimately we're going to be picking two orthogonal vectors, u and v, right, that define a plane. So we have our little bivector here. And then we're going to take some arbitrary other vector, which I guess we could call, let's call it S, and we're going to break S up into a coplanar part, which would be S coplanar, and a orthogonal part, which we're going to call S orthogonal. And we're going to, once we break S up into a orthogonal part and a coplanar part, we're going to start multiplying by bivectors, and we're going to, this split will allow us to exploit these rules, right? Or these rules will allow us to exploit this this obvious split. Okay, so with those two rules in hand, let's move on. So the next preliminary we need to look at before we go deeper into exponentiation is we need to show that a bivector multiplied by the inverse of the pseudoscalar that defines its plane is a real number, right? It shouldn't be hard to show this, but it's worth spending a minute to do it. Now, I did it, again, a hard way. I'll do it a hard way because the hard way is not that hard, but also it illuminates the easy way, I think. So let's figure out, let's just calculate this. We have a bivector between u and v, and we have the pseudovector of its same plane inverse. So let's remember, what do we mean by this? Well, that means I'm going to choose a vector w hat and s hat such that w hat and s hat have the same alignment in the plane as u and v. And we've learned how to do this. We know that we can definitely find w hat and s hat that are unit vectors that are in the plane, and we know that w hat dot s hat is 0. So we've chosen orthogonal unit vectors. And once we've done that, we know that w hat s hat, that's what we're going to define as our pseudovector in the plane. And since we know that a pseudovector squared is -1, which we already just showed a little bit earlier in this lesson, we know that I inverse is just -I in order to make that all work. So I'm going to replace I inverse with minus omega s, assuming, just saying we know we can do it, so we're picking an omega s that are orthogonal, they're unit vectors, and it's a pseudovector for the same plane as defined by the bivector of an arbitrary pair of vectors u and v. So now we just proceed to sort of crunch things out, right? We're going to associate, we'll do an association between, say, this, since it's all bivector multiplication, it's associative. So we'll say, not bivector multiplication, it's bivector vector multiplication. But we'll take this pair and do the appropriate association, and we will get this expression here. Now notice we have a bivector multiplied by a vector, u wedge v, geometric product with w. So where's the trivector, right? This is the contraction part. Where's the inflation part? Well, remember, w is in the plane of u and v, so the inflation part is 0. So we've got this. That's an easy expression. We have, this is a real number, this is a real number, these two coefficients are a real number. So this thing in brackets is a vector. So now we have vector-vector geometric product. So I'm going to do two things. I'm going to switch the order of these two. So I'll put this here and this here. Therefore, we lose the sign, and we distribute s into the situation. So that gives us our next line. And then we do the vector-vector geometric products, right? So that's this standard vector-vector geometric products. Notice that this v and s are in the same plane as the bivector defined by u and v, but it doesn't mean that their bivector is 0. The bivector between them is not 0. If I had u, v, and s, that would be a problem. but I only have v and s. So that just defines the same plane as, well, it's oriented in the same way as u and v is, but it's not 0. So I make that substitution there, and then I make this substitution here, right? And this is simply the vector-vector geometric product, the contraction part and the inflation part. Contraction part and inflation part. And then the next thing I did was I multiplied this stuff out, right? Every time you see a dot product, you're looking at a real number, right? So this contraction, that's a real number. So the product of those two, that's a real number. We have, this is a real number here. Then this times this, that gives you this real number here. And then you have this bivector here. Whoops. You have this bivector and this bivector, which ends up being this guy right here and this guy right here. So those two are bivectors. So that's blowing this whole thing up. Now you need to do a clever observation. If you go down this route, if this is your method of proof, which is sort of the straight ahead, let's just take our problem here and multiply everything out and see what we get. That's rarely the way to really get to the nitty-gritty of these problems quickly, right? It can be done, but you almost always need to see something clever down the line, and we are now actually down the line, and we need to see something clever. And that cleverness is this. U wedge V wedge S. That's a trivector, and that trivector, if we take its geometric product with W, right, what do we get? Well, the first thing we get is 0, right, because this guy is 0. And the reason that's 0 is because U and V are as a bivector define a plane, and S is in that plane. So this guy is 0. So this whole thing is going to be 0 no matter what. That doesn't stop us from blowing it up and completing this geometric product. And when we do that, when we blow up this geometric product, which we discussed how to do, the geometric product of a vector with a trivector is going to be a bivector and a quad vector. But the quad vector will definitely be 0 for the same reason the trivector is 0. So what's left is a bivector. And when you blow this up by taking, S dot W multiplied by U wedge V, and then V dot W multiplied by minus U wedge S, and then U wedge W times V wedge S, right? You end up with this expression. And none of these, this is not 0, and this is not 0. These dot products, U and U dot V and V dot W and U dot W are not 0. V wedge S is not 0. U wedge S is not 0. They both are oriented in the same plane, right? They all lie in the same plane, but they're not 0. But S dot W is 0, because when we defined S and W, we defined them to be orthogonal. That's how S hat, W hat became the pseudovector. So this first term is 0. So that means we know this is 0, and we know, so the sum of all these three must be 0. But since this one is 0, that means the sum of these two must be 0, right? And ergo, it turns out the sum of those two is exactly what we're looking at left over in our calculation. So these two guys are basically 0. So that means that this product we're trying to calculate, this product here, which is this product here, and if you look at this product here, that can actually be written as V wedge U, flip them around to get rid of that minus sign, and W hat wedge S hat, because the geometric product of orthogonal vectors is simply its wedge product. So that I put right down here, and now we see that V wedge U, W hat wedge S hat is this thing right here. And this is the bivector part. The bivector part was what we decided was 0, right? So the bivector part is 0, so that leaves only this real number. So now we know that this expression v wedge u w wedge s is actually equal to some real number, which we could call, say, phi. All right? So what's the next step? Oh, there was one other thing I wanted to show. I said there was like an easy way. And, you know, I probably overstated the case. What I wanted to say, for as far as the easy way goes, is if I look at this, I could immediately jump to right here, right? Because this part is just flipping u and v, so we lose the sign. And this part is w geometric product s because w and s are orthogonal. So I could have immediately just skipped right to here, and I could have then said, oh, well, this is just a bivector times a bivector. I know how to do that. There's going to be a real number part, and there's going to be a bivector part, and the quad vector part is obviously going to be 0 for all the reasons we discussed back here, right? The trivectors would all be 0, not to mention the quad vectors. So I could blow this up, and I would have found that the real number part is this. That's very, we discussed how to do this bivector product before, and this would definitely be the real number. The problem is I would have still ended up with this piece here. So what I was thinking when I said earlier, oh, there's an easy way, I was thinking, oh, we just jump to here and we come up with this. But we don't. We come up with this and this just as well, right? In other words, instead of doing bivector times vector and then vector times vector, we could just do bivector in its full glory. But we would have ended up with this piece here. In this final stage, we end up only with this piece because we've already kind of figured out that this piece is 0 using our extra knowledge of the non-orthogonality. There's no orthogonal component of S or V with the bivector U and UV. So there really is no, as far as I know, no quick, simple way to get here without going through this insightful piece of the proof. Okay, so the next step is to apply this to an exponential. So what I want to show now is I want to talk about this exponential. I want to talk about a real number times the exponential of a bivector. So we're just going to take the exponential of an arbitrary bivector, u wedge v. And the first step to do this is we're going to go to create I for the plane identified or defined by u wedge v. We're going to create the pseudoscalar of that plane, and we've learned how to do that already. And we're going to call that pseudoscalar w hat s hat, just like we did earlier. And then I'm going to take, okay, let's just look at u wedge v. I rewrite u wedge v here, and then I write the pseudoscalar squared, right? Because this is I and this is I, so this both of them is I squared, which equals -1. Oops. So -1, right? So I have this negative sign out here to compensate for the fact that everything in these parentheses is -1. So we basically are just this whole thing all together, right? This in its entirety, let's see, this part here equals 1. So it's just 1 times u wedge v. But now we start using our knowledge from before, and we say, oh, S is in the plane of the bivector u wedge v. So I can commute S with u wedge v. I can anti-commute S with u wedge v. So I bring S over to the right, and I lose the minus sign that was lingering in front. And then W is the same as S. It's in the plane. So I anti-commute it over, and I get my minus sign back. And so what I end up with is WS, U wedge V, WS with this minus sign. And if I take that minus sign and apply it over here, I end up with W hat, S hat, and then U wedge V, I inverse, right? Because I have minus WS over here now, right? So that's I inverse. So this structure is what I now have in the exponent, right? And, well, we can cut to the chase, right? We can say, well, I know that this is a real number, right? So this exponent is actually going to be some real number. This whole thing here is a real number. So this is going to be, and WS, that's defined as I. So this is going to be I times some real number phi. So we've already shown it. I did this before over here on the right. And in this case, I, instead of leaving WS as a geometric product, I blew it up into its wedge form. But it's the same thing, right? It's when you, essentially I blew it up into its wedge form and then contracted it back. But it's ultimately a to the exponentiation of the pseudoscalar times phi, which we can write like this. So the point of this is that I've created a pseudoscalar for some arbitrary plane defined by u and v, and I can do this for any plane. And once I do that, I can kind of get rid of it and call it I. And now you see how everything is complex numbers, right? This is just straight up polar form of a complex number. And this exponential is literally defined by its Taylor series, so we know I can go cosine phi, I sine phi, and I can immediately write a cosine phi, I sine phi. Consider a vector now. Consider a vector, right? So notice that a is irrelevant all here. I think I might have said it was a real number a little bit earlier, but consider a vector. So if it's a vector, it certainly will commute with the cosine part, but if a is a vector in the plane of u wedge v, say it's a vector in the plane of u wedge v, when it commutes, that means it'll anti-commute with this I, right? Because if it's in the plane of u wedge v, it's certainly in the plane of the pseudoscalar w wedge s or w hat s hat. So it's going to anti-commute across this I, which picks up a minus sign. So I can say that if a is in the plane, I get e to the minus I phi a on the left, with e to the I phi on the left. Well, I guess what I'm showing is that this this final term equals a e to the I phi, so that the point is a vector. It neither commutes nor anti-commutes with this exponential, right? It just goes through the exponential, but the exponential changes its sign. You're changing the sign in the exponent. For it to truly anti-commute, you would have to change the sign overall. So it's a slightly different form, but we know how to commute a and e to the I phi. The sign changes in the exponent. And if you did this for a vector b that was orthogonal to the plane defined by the pseudoscalar w and s, then when you try to bring b through, I say this was b now, b and I will straight up commute, right? So you end up with a b over here, and then this has a plus sign, and then you just reconstruct that, and there's no change in sign at all. So now we know how to commute. We now can commute vectors that are in the plane, vectors that are out of the plane with exponentials, e to the I phi and e to the I phi. I guess we say that equals e to the I phi b, and this equals e to the minus I phi a. So we've learned about these two commutation rules. So that is all for today. So we are now set up understanding just a lot more comfort, I think, with exponentiations. We understand exponentiations with respect to bivectors. We understand that if you have a bivector, that bivector, of course, defines a piece of plane, and then that plane can be given a pseudoscalar by a simple process that we've gone through a couple times already. And we understand that we get real numbers out of bivector products when the two bivectors, even if they're not the same bivector. Because I think we showed in the last lesson that if we take a bivector and square it, we'll always get a real number because we'll have this beautiful cancellation. Well, in this case, we'll get a real number even if they're just in the same plane with each other, because they're essentially equivalent up to a real factor, right? Any two bivectors that define the same plane are the same bivectors up to some real factor between them. So we can always write these bivector exponentiations as an exponent of the pseudovector designed for the plane. Now, I've called it I here, but this I is very particular to this particular plane uv. So to be fair, I mean, you might want to, if you wanted to be really careful, you might write this I as I uv, right? Just to make it clear that that's the pseudoscalar for that particular plane. Or you could just leave it as ws, understanding that W is orthogonal to S, right? See here, that orthogonality is automatically implied by the fact that you're calling it this, pseudoscalar basis vector. Here, you have to sort of remember that W dot S is 0. And of course, this exponential always is defined by its Taylor expansion, and so we can always use this Euler form. And we now also remember about our commutations between things that are in the plane and things that are out of the plane. So in our next lesson, we're going to take all of this and we're going to use it to identify how to rotate vectors. Okay, so I'll see you next time.